Okay, hello everybody. My name is Vincent or UZ Leo. So today I'll be lecturing about nonlinear optimization and its real-world applications. So before I get into the topic, I want to briefly introduce myself a little bit. So I'm currently a third year math student majoring in math application in finance and economics. I personally find this nonlinear optimization is very useful because in the finance or even economics, we usually have to deal with the problem to either maximize our profit or minimize our cost. So optimization is a very useful topic, and there's so many useful tools from mathematics that we can use to achieve finding maximum values or the minimum values. Yeah, let's get started. So before we get really deep into the topic, I wanna give a fundamental knowledge about nonlinear and optimizations. So because for myself, I thought math was really useless, to be honest. Uh, I didn't find it really helpful until I get into this major, and I find it's math tools like optimization and the functions can be very useful and benefit our current life or real life. So I think it's really I think it could be useful to make as many people as possible to understand what I'm trying to talk about. Even though you have no solid math background, you can still understand everything. Yep. So I want to define two terms here. So the first is nonlinear. So basically, what we see now a linear function would basically look like in this format. That is y equals to ax plus b, and here we have x and y as the parameter. So as we can see here, for example, we take this function x equals to 1 and y equals to 1. We have 1, 1, obviously. But every time we increase x by 1 here, we have y equals to 2, which the increment is the same amount. So that's basically the definition of a linear function, is that every time you have this one parameter increased by a certain amount and the other parameters follow the same patterns. So that's the negation of linear is basically nonlinear. That is, for example, I would take y equals to x squared as an example. So here we are at the second quotient. So if we take a look at this point, oops. Oh, so this point is 1, y equals to 1, and x equals to 1. So we have 1, 1, but however, when we take this point, which is y equals to 2 and x equals to uh, square root of 2. So we can see square root of 2 is strictly smaller than 2. That is one y increased by 1 unit. X does not equal to the same unit, or it doesn't follow the same increasement patterns. So this is basically nonlinear. And here we have the formal definitions. So how do we define a nonlinear function, or what can we say about nonlinear function? Is that one variable change has no proportional or direct effect on the other variables, which is exactly what I've the examples that I showed here. This one is just it's linear, follow the format of y equals to ax plus b. And this is the typical example of a nonlinear functions. And now we're going to talk about a little bit about optimizations. So I will show this graph right here. This is basically the 3D dimensions for linear functions and nonlinear functions. As we can see, the first one is um x squared plus y squared equals to z. So this is basically the first the 3D version of a nonlinear functions, and this one is just simply x plus y equals to z. So as we can see here, um, it's the first one does not just like what we said, the variable changes. For example, when xy changes, the z change does not has no proportional or direct effect. Yeah, so optimization is basically when we use the math techniques to solve for the best possible solutions, probably subject to certain constraints. We take or the first graph as or examples. If we try to maximize, okay, so optimization is just basically finding maximum values and minimal values. For example, if we want to find the minimal values for the first graph right here, which is exactly what we can see here. It's just the origin. The origin is just 0, 0, 0. So this is the minimum value that we can find. So by using math tools that can allow us to find this certain point, which is the global minimum values. And that is the optimization. It doesn't necessarily have to be maximum values. It just have to be, it's more like finding extreme values, either the maximum values or the minimum values. And also, I wanna talk a little bit about the application a little bit, just to give a hint. So, optimization can be used in many fields. For example, if you're running a company and your goal is to determine the quantity of the goods to sell under certain conditions. For example, your budget constraints on the market, and optimization can allow you to determine the quantity of good that you can sell to either maximize your profit or minimize your cost. And as we know, there are many math techniques that can achieve uh, basically helping us to find the optimization point. I will introduce a couple of them. So the first method is known as Lagrange method, or you can call it Lagrange multiplier. This method is basically has something to do with the first order conditions. We set our equation equals to 0, then we find x star, which is the optimized point that we can find. And the second method is called a gradient-based method, which is the ones that we talked about during the lecture. It requires a lot of knowledge about Jacobian and Hessian matrix. The third method is known as Newton method. It's more like utilize both gradient and Hessian matrix to find to allow us to optimize the function. And lastly, but not least, the method is the interior point method. I believe we also talked about it during the lecture time. So it requires you to have really strong understandings, either geometrically or functionally understanding about what is the interior point and what is the boundary, not only in the first or the second dimension, but also the third, maybe the higher dimensions. And today we are going to just only focus on one because we only have 15 minutes. I want to get really deep into the topic, so I only chose one to introduce, which is the method one. known as the Lagrange method. Yep, let's get started. So we will introduce Lagrange method from two perspectives. So the first one that I chose is math intuition. I think understand the back mechanism is very important. And secondly, we're gonna talk a little bit about some practical use, how this nonlinear optimizations can benefit our current life. Specifically, how does the Lagrange method can help us to solve some real world problems. So to begin with the math intuition. So I think Lagrange method is a very powerful mathematical techniques to solve optimization problems, specifically with constraints. To understand the Lagrange method, we will establish some groundwork. So as we talked about in the previous, Lagrange method is always used to solve functions with certain constraints. For example, we take a look at this graph here. So here we have f of xy equals to x squared times 1. That is the function that we're trying to maximize. So here, let me just write. It's usually this format, max. And we need to subject to its constraint. In this case, is this unit circle, x squared plus y squared equals to 1. And this is how we actually write this is our setup basically. So how this actually works is that if we because since we need to optimize the function with constraints, so we have to consider both functions. So when you maximize the f of x, y, and you also have to be in the domain of your constraint, which is in this case the unit circle. That is every time we can see here, these lines are actually the contour lines. So it doesn't necessarily, perhaps this case can be 1, and maybe y equals to 2. The graph perhaps looks like this. So it's more like a contour lines. And what Lagrange method does is basically we take a look at each contour line, and we look at the interactions where occurs at the boundary of the unit circle, which is when we find I'll use purple, pink. So when we find the point, just like this white line, where it only touches a little bit here, that is when the function is maximized. So we're basically finding the lines like, for example, this is our budget constraint, and this can be our utility functions, which it's more like economic terms. So we are finding the point where we can maximize our function, but also within our constraint. So to sum up what I've just said, so Lagrange method, we usually have to set up a function. Perhaps this is gonna be f of no, here. So we usually set up the function that's called 3 dimensions, f of x, y, and z, that we want to optimize. Subject to constraint, here we call it the function g. g of x, y, z. So since here we're working on 3 dimensions, so the parameters that the variables that we use is x, y, z. The function respect the object, which is f of, which is this one, respect to the variables that we need to maximize. So the Lagrange method basically introduce a concept of Lagrangian, which is defined as the function L here. And this is the Lagrange function. And the lambda here is called a scalar parameter. It's called Lagrange multiplier. So the Lagrange combines the object functions with the constraint functions, and it allow us to transform the constraint optimization problem into an unconstrained ones. So that is when we just simply have to. It's more like we combine the object function with its constraint. So we combine to one function and we maximize it, so we can get the result where not only maximize the objective function, but also within the constraint what we have. So then it's finding the maximum or minimum value is it's just what we have learned. It's we taking derivatives where, so the intuition is more like if we have this function, derivative is more like the growth rate. So here you have the growth rate like this. When you reach the maximum peak, you don't growth anymore. So your growth rate is 0. So it's more like a intuitionally understand. It's more like that. So same thing here. We take a look at our first order conditions respect to each parameters, each variables. So what we basically do is we take partial, because since we're doing 3 dimensions, we take partial derivative respect to each variables, and we need to set it to 0. And also, therefore, when we when we find when we set it to 0, we are able to find the critical point of the Lagrange function that's like satisfy the constraints. And when we solve, because after we solve these first order conditions, we will have like 3 system of equations. We also need to solve that to find the critical values for each variables that allows us to re-put into the object functions, so we can have the optimization result. So I will demonstrate with examples here. So just like what we have talked about in the previously, we will now well, I'll show a, oops. We will now show an examples. So let's do the setup first. So here we are trying to maximize f of x, y, z, subject to g of x, y, z equals to x squared plus y squared plus z squared equals to 1. So we first of all need to set up to combine the object function to the subject constraint, which is we have to set up a Lagrange function here. We call it L equals to it's basically f of x. It's basically f plus g. But here we have to put the minus, make it become a minus. So here, this is the function that we're trying to maximize, trying to optimize, and we need to subject to x, y, z. Since we're here, we're talking about 3 dimensions. So let's take a look at the solutions. No, before we get into that, I will generally talk about its general process. So when we have these functions, this function is already it's already combined the object function with this constraint. So what we have to do now is we need to maximize this function subject to x, y, and z. How do we do that is as what we were talking about. We take the first derivative and we solve for the critical point x, y, and z. So we set it to 0 and we find the critical point x, y, z. That is going to be our optimized point. And if we need the specifically value for the function, like when we reach the maximum value, what f will equals to, so then we will just plug in x, y, and z, and we will solve for the Lagrange. So here's the solution. So in this case, we set L, X, Y, Z, and also with the Lagrange multiplier lambda, and we equals to X plus Y plus Z plus lambda X squared plus Y squared plus Z squared minus 1. So here's the function that we're trying to maximize, max subject to X, Y, and Z. And this is what we're going to do. So we first of all have to consider the first order condition, which is we take the first partial derivative subject to each variable. That is, we first of all take subject to x. That is, if we take a look at this function right here, we take a look at the partial x, the other variables we treat it as a constant. So this part, we only have one x. We take the derivative with respect to x. We get 1, and here we have a lambda within the y squared and z squared and minus 1 we treat as a constant, which when we take derivative with respect to x, it will all disappear. We will have x squared. Don't forget there's a lambda right there because since it's times, so it's gonna keep it like the way it is. So we have the first derivative already, but we need to set it to 0 to reach the maximum point. That is maximum or minimum point to be like strictly. So we set this equals to 0. And now we take this, we keep the same process for a partial y and to partial z. And here it's we can take the other derivative that is respect to lambda. So this process here is just basically respect to lambda. So this process we will eventually have x squared plus y squared plus z squared minus 1. We set it equal to 0. How? Because when we're taking partial derivative respect to lambda. The other variables we treated the constant. So for x, y, and z, it's all constant. These are also constant, but here we have a lambda. We take derivative, a equals to 1. At times to these constant, we still get these constant. And later on, we set it to 0. And here now we have a system of equations that we need to solve. Later on, we solve for x, y, and z just to save some time. So I already have the answers here. So we will have there equals to 1 over square root of 3. So this is the optimized point that we have, the critical point. That is x star. Oh, it's actually here. So x star, y star, z star. This is the, so we finish the Lagrange process. Also, we can the first order condition doesn't necessarily have to be the maximum value. It could be minimal values as well. And in that case, we have to solve we'll have to consider the second derivative conditions, which to determine whether it's maximal or minimal values. But when we stop here, this is going to be our optimized point. Then we're finished. Then we just have to consider the second derivative conditions to verify this is our optimized point, whether it's max or minimum, but it is an optimized point. If we want to determine whether it's maximized or minimized, you just have to do the second order test. Yeah, then if you want to know the specific value for the function when we reach this point, what is specifically value that this function will get, we just simply have to prep these critical point into the object function, which is x plus y plus z, and we will eventually get this function. It's approximately equals to 1.732. And here is our math part. We will now begin with our practical use, because this is what we mainly gonna focus on. Okay, so now let's look at some of the application of Lagrange method. Specifically in the eco field. So before I get started, I want to ask a couple of questions. For the participant to think about, so we can have a better understanding of this application use. So the first one is, what does consumer do? Like, what do consumers do in the market? And do since we're gonna apply the Lagrange method into the real world problems, so we have to think, how does it fit the models? So does the economic model fit the Lagrange method? Therefore, we have to consider two things. The first is what is our constraint? And the second is, since we're optimizing a function, therefore we have to also consider what are we trying to maximize? I'll just say maximize or minimize, since we're finding the optimal point. So there's just this one thing, the economic models that fits the Lagrange method perfectly, that is when that is using utility functions and the budget constraint to maximize how many goods, the bundle combination that the consumer needs that maximize their utility. So I'll just introduce two terms here. So the first is a utility function. Oh no, before we get into that, there's just this one thing. So there is in mathematical, we call this contour line. So, but in economic, we call it indifference curve. So that is stands for IC. So every time we see a contour line, for example, I'll name this function as a function f1, and f1 equals to c1, and this function equals to this is f. It's still the same function, but this function equals to c2. So since it's the same function, but with the different contour lines, so these two are just basically the different two contour lines. So that means at this point, all of the x, y values, so we define f as f of x, y, to make this more applicable, we will put this as x1, x2, and x1, x2 stands for good one and good two, the quantity of the good. So this function is basically means at this point, at any of the point on this curve, that the different combinations of x1 and x2, they always have the same value. So in economical view, these two goods can bring the same utility to the consumers. Like these 2 points, point A and point B, can bring the same utility to the consumers. So it's basically equals to contour line. And the other concept that I want to introduce is the budget constraint. So we know for the Lagrange method that we need to have a budget constraint. Same in economics, because consumers will always have the limited amount of money to spend on a certain good, that to maximize their utility as more as possible. So as now we can see, the function is perfectly fit into Lagrange method by combining the utility function. We'll call u of x, y, x2. This is our utility functions. And our budget constraint is going to simply be, which just stands for budget constraint. It's just going to be our g of x. And this utility function is going to be f of x, as we were talking about in the math part. So the fundamental, this as same as in math. So when we have a fixed budget constraint right here, and these curves represents the utility that consumers can get, C1, C2, and C3, just like the contour lines. We're trying to find, let's look at the beginning. So we're just like this question right here. We're trying to find the intersections where occurs at the boundary of the target function and the constraint, which is this point. So at these point, the function can be maximized based on its constraint. Same in economic views. So here we're trying to maximize our utility function u x1, x2, and subject to the budget constraint. That is, we're moving along with this curve to these directions to find which bundle, for example, this is bundle star, x1 star, and x2 star. And at this bundle, it is possible to achieve because it's in the budget constraint, and it is also the greatest utility that the consumers can get. So this will be really good explanation of how the economic be fitted into the Lagrange method questions. And now we understand how does the economic model can fit into the Lagrange method, and for us to find the optimal point. And now we have to do the economical setups to, because eventually we're going to solve for the best bundle that the consumers will be satisfied of for. So therefore, we have to set up a function to connect the budget constraint with the utility functions. So our utility functions can be various, which means they can be different. They can simply be x squared, plus y squared, and plus whatever that they want to. So utility function can be a lot of different type. So in here we'll just say x1 plus x2. And our budget constraint is more like a fixed. It has like a standard formulas. That is, budget constraints basically or cost. How many monies that we are planning to spend. For example, if we trying to buy two goods, x1, x2 stands for maybe shampoo and body wash. So we only have $100 spending for these two products, and this is the budget constraint we have. But how do we represent in terms of X1, X2, which means how many money will we spend for buying shampoos and the body wash? It's basically the quantity of the goods that we will consume times the price of the goods. Since we're having two goods here, so X2 times P2. If we have multiple goods, for example, the other things, then we just have to plug it in, like X3 times P3, and this is going to be our budget constraint. Since we only have $100, therefore our budget constraint is this. And now we have the function that we're trying to maximize. And we have our constraint functions, then we can use our Lagrange method to combine the function into one function, which is we have a Lagrange functions here, x1, good 1, good 2, and don't forget our Lagrange multiplier lambda. So as we were talking about, the function is u of x1, x2, plus the Lagrange multiplier times our budget constraint, which is x1 times p1 plus x2 times p2. Now we're trying to maximize this function. Therefore, we have to consider our first order conditions, which is OC we have our Lagrange subject to x1, Lagrange subject to x2, and our Lagrange function subject to the Lagrange multiplier lambda. So this will eventually get us, since we don't have a specific functions here, but later on we will introduce a real world problem to solve for the specific functions, which is very similar to what we did in the math part. But just to show you guys how this the application how this Lagrange method can be used in the real world. So I've decided to introduce a real real world problem that we can solve. So here's our first order conditions, and we set it to 0. And now we have to, this brings us a system of equations that we need to solve for x1 star and x2 star. And based on the given, since the price is given, we know the price P1 and P2. We put P1, P2 into the system of equations, and we solve for x1, x2. Therefore, the optimal bundle that you will have is x1, x2 star. Then when you solve for the system of equations, you will have an optimal bundle which maximize your utility while having, well, like, how do I put this, within the limited money that you can have. This bundle can make your as satisfied as you can. It's basically maximize your utility. Geometrically, it's more like you have your budget constraint, and you have x1 and x2. The x-axis and the y-axis, this basically represents how many goods you can consume. For example, you have 5 here and 6 here. That means you can have either 5 of good 1 or 6 of the good 2. And these are the endowment point and any combinations of the goods you will consume. This red area is basically the affordable affordable goods that you can consume. And while we have the utility functions, utility function can be looking various like this way, but does it maximize our profit? No, does it maximize our utility? Apparently no, because at this point, um, can we afford it? It's in the constraint, so definitely sure. But does it maximize our utility? I don't think so, because we also have this curve. And we can see C2 is bigger than C1, therefore C2. So any of these bundles can make us happier than consuming this X1 X bundle. Therefore, we have to, by Lagrange method, we found the optimal point, which is the intersection between between the utility functions and the budget constraint, which is this point. And this point is basically the bundles that we consumed. Therefore, is this one. We will use some real world problem to introduce this concept a little bit more, so we can understand what's going on right here.